In this video, we're going to be talking a little bit about the basics of graphing. It's going to be one of two videos that talks about some of the foundational ideas behind graphing. You'll notice that for this video, I've prepared what's called a rectangular coordinate system. So what I have drawn here is just that, and I hope that for the most part, it's familiar. So you've got two axes. The x-axis and the y-axis is what they are typically called, although any coordinate system that has two axes, a horizontal and a vertical, is going to be using the ideas of the rectangular coordinate system. I'm going to mark a few points on here just for us to sort of be aware. So the point that is the most important point on this whole system is the point where the two axes intersect. Every point in this system is going to have two coordinates. The x-coordinate, which is the first one, and the y-coordinate, which is the second one. And it all stems from the origin, whose coordinates are 0, 0. So, for example, if you decide to go right 3 units and up 2 units, right is the positive direction, up is the positive direction. So the coordinates of this point are 3, 2. If you decided to go, say, left 1 unit and then up 4 units, left is the negative direction on the x-axis, y went up, so that's the positive direction, so the y-coordinate is positive 4. And so on. So up is the positive direction for y, down is the negative direction. Right is the positive direction for x, left is the negative direction. So that is how we plot points. So for instance, what would the coordinates of this point be? Well, to get here from the origin, you have to go right 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5. So the coordinates of this point are 5, negative 5. And you'll notice that this is called the rectangular coordinate system, which might suggest to you that, hey, maybe there are other coordinate systems as well. And it's true, there are other coordinate systems. We may even get a chance to talk about one of them. It's called the polar coordinates. We may get a chance to talk about them. If not, you will certainly talk about them in your trigonometry class, which you would take next semester. So before we start really playing around with the rectangular coordinate system and kind of saying more about it, I want to say the basics of graphing, kind of what is a graph. So a graph of what, right? So for our purposes, we're always going to be looking at the graph of an equation. And since the rectangular coordinate system has two axes, our equations are always going to have two variables in them. So the graph of an equation in two variables consists of all of the pairs x, y that satisfy the equation. So, for example, if the pair 3, 2 satisfies the equation, and we'll play around with it to see what that means in a minute, that would mean that the point 3, 2 is a point on the graph. Okay? So let's try a couple of examples. So say that we're going to ask the question, is 3, 2 a point on the graph of 2x minus 3y is equal to 0? Well, so again, 3 here is the x-coordinate, y is the y-coordinate, 2 is the y-coordinate. So if I replace x with 3 and y with 2, I'm looking to see whether what I get as a result is 0. Well, what do you all think? 2 times 3 is 6, 3 times 2 is 6. Sure enough, 6 minus 6 is 0. So yes, 3, 2 is a point on the graph of this equation. Now, maybe we want to find other points on the graph of this equation. So, how would we do that? Well, we can guess and check. Let's turn it into an example. Find another point. On the graph of this equation. So you could guess and check. Just kind of give it a shot. See whether, I don't know, 4, -2. Right? I kind of made that up off the top of my head, mostly so that we could see an example of something that didn't end up working. So we would have 2 times 4 minus 3 times -2. And we're seeing if that's equal to 0. Well, this would be 8 plus 6. And I think we can all agree that's not equal to 0. So no. That's an example of a point that's not. And I hope you'll agree with me at this point that that could be a really time-consuming and frustrating process. Just kind of guessing and hoping for the best. But rather than guessing, an intermediary step is to say, well, I want to see if there's a point with a given x coordinate. So let's fix x and solve for y. So you can fix x to be anything you want. Worst case, there isn't a y that would work. But in the case of an equation like this one, which is a linear equation, you'll actually notice that for any value of x, you'll find the value of y that works, which actually hints at something about like domains and types of graphs, which we'll talk about later in future lessons. So for no particular reason, I'm going to fix x to be -2. I want to do a negative number so that we have a little bit of experience. So what do we have? So I'm actually going to write it in red. So 2 times -2, that's my 2x. Minus 3y is equal to 0. So I'm solving this for y. 2 times -2 is -4. Minus 3y is equal to 0. So I'm solving this for y. One thing you could do is add 3y to both sides. And so what you'll get here, dividing both sides by 3, is that y is -4/3. So we just generated another point that's on the graph of this equation. And that point is -2, comma, -4/3. Okay? I don't want to make you believe that you always have to fix x and solve for y. So let's try fixing y and solving for x. And it really is 100% up to you. You can fix either x or y. You can fix them to be whatever you like. So for this point, let's say let y be 5. I'm making these numbers up. There's nothing significant about the number 5 in this example or the number -2. So we have 2x, which is 2 times 5. Oops, we fixed y, not x this time. So 2x minus 3y, so 3 times 5. And we want that to be equal to 0. So we have 2x minus 15 is equal to 0. So now we'll add 15 to both sides. So 2x has to be 15. And then we would divide both sides by 2. So we end up with, if y is 5, x has to be 15 over 2, which is 7.5. So now we have 3 points. And I want to take one more example, okay? Because this is kind of a, first of all, I want us to see sort of what shape we get. And for that, I want to have a few points. But also I want to get an opportunity to talk to you a little bit about intercepts. So intercepts are a really, really interesting collection of points when you're talking about graphs of equations. So intercepts can be x-intercepts. And I'm going to put x-intercepts possibly plural, right? Because not every equation that we look at is going to have just only one x-intercept. And the same is true for y-intercepts, right? Some equations that we'll explore, when you go to graph them, they actually have more than one y-intercept. So again, this is one of those things that I kind of hope that rings a bell, so that when I start talking, I don't need to go into a lot of detail for it to start to come back. I'm going to go back to my rectangular coordinate system picture here. Intercepts are points that are not floating out in space, but they're actually on the axes. So like this point here is on the y-axis. So if you're describing movement from the origin to get to this point, do you notice how you're not moving side to side at all? You are going straight up from the origin. So the origin has coordinates 0, 0, and we didn't move side to side from that. Moving side to side would have impacted the x-coordinate, and since we did not do that, the x-coordinate stays 0. Now, we went up, so that's the positive direction. We went up 1, 2, 3, 4, 5, 6, 7, 8, 9 units. So the coordinates of this point are 0, 9. So points that are on the y-axis result by moving only vertically, not side to side from the origin, which means their x-coordinate is 0 and their y-coordinate is either positive or negative depending on whether you moved up or down. By that same token, let's think about a point that's on the x-axis, like this one, okay? So again, you'll notice that if you were to describe how you got to this point from the origin, you didn't move up or down at all. You only moved in the horizontal direction. So again, the y-coordinate of the origin is 0, and you did not move up or down from the origin, which means that you did not change the y-coordinate. So if a point is on the x-axis, its y-coordinate is 0, and then its x-coordinate is whatever it is, depending on where the point is, but in this case, we moved 1, 2, 3, 4, 5, 6 units to the left, so the x-coordinate of this point is -6. So those are the intercepts. The reason they are called the intercepts is that when we're looking at the graph of an equation, the intercepts are where the graph crosses or intercepts the x and y axes. So let's find the intercepts of our equation here, 2x minus 3y is equal to 3. And incidentally, this is how you find the intercepts for any equation. So of course, in this lesson, we're looking at a fairly simple equation, 2x minus y equals 3. It's linear, 2x minus y equals 0. It's linear, one side is 0, the coefficients are nice and whole, but the concept applies to all equations. And you'll notice in your homework, for homework 2, you are going to be given a couple problems where you're asked to find the intercepts where it's a slightly more complex equation. But the idea is the same. For the x-intercept, and you'll notice I frequently abbreviated x-int, we let the y-coordinate be 0 and we solve for x. So let y be 0, solve for x. So in this instance, we have 2x minus 3 times 0. That's just 0. So 2x is equal to 0. And now divide both sides by 2. Oh, so the x-intercept of this graph is actually the origin. That will happen sometimes. What this means is that this graph passes through the origin. Some graphs do, some graphs don't. Just for the sake of saying we did, let's also look at the y-intercept of this graph. So for the y-intercept, we let x be 0 and solve for y. And you'll notice the same thing, that if x is 0, we have 2x, that's 0. Minus 3y is equal to 0. We divide both sides by -3. Oh, so y is 0 also. So as it turns out, and this does happen sometimes, this whole equation has one, when we look at its graph, it has one intercept to speak of. It crosses the graph at the origin, and that is the only place where it will ever cross either of the axes. So now that we've gone through all of this process, let's go ahead and use the points that we found. So we actually have quite a collection. We have 3, 2. We have -2, -4/3. And we have 7.5, 5. And lastly, we have the origin. So we have quite a collection of points. Let's plot them all. And let's see what the shape of the graph is. So I'm going to go ahead and erase these some of these points, because I don't want them to kind of crowd my graph here. So there we go. So I'm going to go ahead and draw my axes back in. There we are. Okay. So look, I've already got 0 and 3, 2 plotted. So those are 2 of the points, my origin and my 3, 2. Now -2, -4/3. So I'm going to go 2 left. Now, -4/3 is like -1 and 1/3. Some of you may find that helpful to write out. So it's -1 and a little bit. Okay, so we have -2 and then -1 and 1/3. So it's about here. You may find it helpful to label your points, but you'll also notice that sometimes that gets a bit crowded, so use your judgment. And then lastly, we have 7.5, 5. So 7.5 means we go 7.5 units to the right, and then 5 up. So 1, 2, 3, 4, 5, 6, 7.5. So that's about there. And then up 5. 1, 2, 3, 4, 5. So there are my 4 points. So as you're looking at them, what do we think we see? I think we see that they're all collinear. They all fall on the same line. And in fact, the equation we're looking at in this example is called a linear equation, which means its graph is a line. Now, of course, we want to do our best to have a nice line with no bends in it. If you have a ruler, that will be fantastic. If not, that's okay too. So in particular, what we're seeing here is not only is this red line the line that holds on at all the points that are on this equation, but if I pick any point that's off of this line, like for example, 4, -2. So 4, -2 is a point that we determined was not on, did not satisfy this equation, and sure enough, it is not on this line. And we can be confident that any other point, like -1, 2, or any other point you want, you know, -3, -5. Any other point that is not on this line will not satisfy the equation 2x minus 3y equals 0. So this is a really quick basic overview of some of the fundamentals of graphing, including the idea of intercepts. This should get you a lot of the tools that you need to be talking about problems in homework 2. In our next and final video for this week, I'm going to go over a few common shapes of graphs for equations that are not linear. So stay tuned for that. See you next time.